Hello everyone and welcome back. We are on our 8th review video and this one is super important. As you can see, I have some descriptives here. Every single exam has had an area and volume question on it. Now, sometimes they look different, sometimes they're a little bit strange what they're asking, but in general, if you know the formula for the area between two curves, if you know the formula for volume, when you rotate a solid around the x or y axis, and if you know the formula for finding the volume when you are building cross sections perpendicular to the x-axis up on top of a region, then you will be in good shape for 9 points on your exam. Okay, so you want to make sure that you know how to do this because every single exam, it's on there. So we've already practiced this a lot. We're going to do 2 in this video. Do a couple more in class, and we'll hit some more in the review classes to come. So let's get started. Okay, the first question is 2013 number 5, and this is a without calculator. So you are given 2 curves here. F of x equals 2x squared minus 6x plus 4, and you're given g of x, which is 4 cos 1/4 pi x. R is the region bounded by the graphs, and you are first asked to find the area of R. So we definitely have to be able to look at f of x and g of x and determine which one's which. So just from my knowledge of quadratic functions, I know this is a positive a, so positive x squared, which means it's an upward facing parabola. So that tells me right away that this bottom curve is f of x, and then that means that my top curve here is cosine, which again makes sense because you can see it has an amplitude of 4. Cosine starts, crosses the y-axis at its maximum, and then comes down from there. Okay. So we have that. Now we're ready to go ahead and find the area. Well, area is simply the integral from a to b of upper minus lower dx. Okay, so basically you're looking at your 2 curves and you're identifying your upper and your lower, and you are drawing in just a straight perpendicular line with the x-axis, okay? And we're just saying we want the distance between the curves, which would be upper minus lower. So I'm going to go ahead, and you can also, they're very nice in that they have given you your A and the B in the picture, okay? So your A here is clearly 0, and your B is right here at 2. And so I can say that my area is equal to the integral from 0 to 2 of g of x, which is 4 cosine 1/4 pi x, minus my f of x, which in parentheses, make sure you put this in parentheses, is 2x squared minus 6x plus 4, and then dx, so that whole thing. Okay, so we've talked about doing this before. Now, this is a no calculator question, so sometimes when you have area and volume ones, they are with calculator, which of course is much easier. You just need to know the formulas, but then you'll have to do some different maneuvering with your calculator. These ones, you have to really know your rules because you're going to be doing the integral, and that's where you're going to get a lot of points for these questions. So this first one here, I'm going to go ahead, and if I'm doing the integral of a difference, we've talked about this before, especially if you notice that in one of your 2 pieces, so in this first piece, I have to use u substitution because my angle is something other than just x. But I certainly don't need that u substitution for this trinomial over here, for that polynomial function. So I'm going to go ahead and split this and say that area is equal to the integral from 0 to 2 of 4 cos 1/4 pi x dx minus the integral from 0 to 2 of 2x squared minus 6x plus 4 dx. Okay, so now I have 2 separate kind of problems to solve, and then when I put them together at the very end, I'll have a complete answer. Okay, so let's get started on figuring out the solution. So I'm going to slide this up because this is all I need from this point forward. Okay, now I'm going to work this through, and I'm going to work on the left-hand side first, and then I'm going to work on the right-hand side, and then I'll put my answer together at the end. So just so that I don't get confused here. So on the left-hand side, like I said, I'm going to need a u substitution. So off to the side, I'm going to say u is equal to 1/4 pi x. Du is then 1/4 pi dx, or pi over 4. So if I want to get rid of that to solve for dx, I would say that's multiplying by 4 over pi du equals dx. Okay, so now that I've identified u, I want to go ahead and rewrite my integral in terms of u, but that also includes the bounds. So I need to put in my lower bound, which would be 0, so u 1/4 pi times 0, which of course is just going to be 0, and then my upper bound is 1/4 pi times 2, which 2 times a fourth is going to be a half pi. So when I write this out, I'm going to say the integral from 0 to pi over 2 of 4 cosine u, and then instead of dx, of course, I have 4 over pi du. All right, so my constants, my 4 and my 4 over pi, they can be brought out front, and I can multiply those, so I get 16 over pi. And then the integral of cosine u is, of course, sine u from 0 to pi over 2. Okay, so I have 16 over pi sine of pi over 2 minus sine of 0. So then it's 16 over pi, sine of pi over 2. So if I think about my sine curve over here, my sine curve, whoops, looks like that. And so at pi over 2 right here, I am at my maximum of 1. So I would say that this is 1 minus, and of course sine of 0 is 0. So this is just 16 over pi. That's the left-hand side worked out. All right, now the right-hand side. So this one should be a lot easier. Just a straightforward polynomial here. Okay, so I can go ahead and take the integral of it right away. So minus 2x cubed over 3 minus 6x squared over 2 plus 4x, and that whole thing is from 0 to 2. Okay, so I'm ready to go ahead and plug in my upper and my lower bound. So I would have 2/3 times 8, which is of course 16/3, minus, the 2 goes into the 6 here 3 times, so 3 times 4 would be 12, plus 4 times 2 is 8, and of course this is all going to be minus 0 because they all have x's. Put in a 0, you get 0 back. Okay, so minus, let's see here, negative 12 plus 8 would be negative 4, which of course with the denominator of 3 would be negative 12/3. So I'm going to have 16/3 minus 12/3, which is going to give me minus 4/3. And so my final answer for this part A is 16 over pi minus 4/3. Okay, this question obviously involved a lot of work for us to go through, a lot of calculation. So as far as where the point breakdown is, all of part A was worth 4 points. 1 was for the integral, just the setup. That would be right up here. Okay, so 1 was up here, writing the correct integral expression. The second one was for, I'm sorry, the next 2 points were for the antiderivative. And I would imagine that would be getting to here and getting to here. Okay, just taking the antiderivative of both sides. The third point is for the answer, so that's, I imagine, putting in your bounds, subtracting, all this fraction work, and ending up with 16 over pi minus 4/3. So 4-point question. All right, let's move on to part B. Okay, oftentimes when you have a part A that requires a lot of work like that, and it's a non-calculator part question, the second and third part will just be to set up an integral expression, but to not actually solve it. So that's what happens here. We're asked to write but not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 4. So I'm just going to go ahead and draw in that horizontal line for myself. Okay, so that is a little bit off, but we get the idea. Okay, so that's my line y equals 4. And the idea is that we're going to rotate it around that. Okay, so we're going to spin it around, up and around that. So when you draw in that line, and you can tell here you have 2 curves that you're going to be rotating around. So clearly it would not be forming a solid. You're going to have a big space in between. And so this is when you need to use the big R and little r. So I'm going to draw in just a line perpendicular to the axis of rotation that goes all the way through my solid. through both curves, okay? And so what I now have is my big R, which goes all the way between the whole thing, and my little r, which just goes from the axis of rotation to the first curve I hit, okay? So, and I am rotating around a horizontal line, so everything is in terms of x. Okay, so when you rotate around a horizontal line, everything is in terms of x. That means the equations are in terms of x that you plug in. That means that your bounds are in terms of x. So I'm going to be looking at for the bounds on the x-axis. And that obviously means you're doing dx at the end. Okay, so in general, the volume of a solid that gets rotated around an axis, a horizontal line, is going to be pi times the integral from a to b of big R squared minus little r squared dx. Okay, so let's go ahead and plug in what we know according to this problem. So volume equals pi. Anytime I'm revolving, we're going to have that pi out in front. The integral from, remember I said you go to your x-axis to find your bounds. So from 0 to 2 of big R, now it's upper minus lower. Okay, so it's, what's your upper curve? Well, that's that purple line, and that's 4. Minus my lower is all the way down, and it's the quadratic. So I'm going to put that in parentheses because I need it to be subtracting all of it. So 2x squared minus 6x plus 4. Okay. And then squared. So that's your whole upper squared, your big R squared minus little r is again starting with 4, but subtracting away the 4 cosine 1/4 pi x, again squared. And then at the very end, I'll squeeze in my, dx. Okay, so that is the formula, and that is worth 3 points. 2 points for the integrand. And again, I don't really know how they break that all down, but I would imagine 1 point for kind of the big R squared and 1 point for the little r squared. I don't know if you forget the squareds, maybe you get 1 out of the 2 points, but you have everything else right. I'm not exactly sure, but 2 points for what's this piece of it. Okay, and then 1 point for the limits and the constant. So the constant is your pi, and the limits are from 0 to 2. All right, let's move on to part C. Okay, part C is another one where they're asking you to write but not evaluate. So the region R is the base of a solid. Whenever you read this, you know you have one of those cross section. And as soon as we know we have a cross section, we have a specific volume formula to follow. For this solid, each cross section perpendicular to the x-axis is a square. So perpendicular to the x-axis is a square. So again, I want to be very confident on my formulas in general terms before I go ahead and try and do this. Again, perpendicular to the x-axis, this means everything's in terms of x. Okay, so these are the problems where it's volume equals, we're not revolving or rotating anything, so there's no pi. It's the integral from a to b, and again, those are in terms of x on the x-axis, of my area of my shape, okay, dx. It's that simple. So I just have to say, what's my shape here? My shape is a square. So these are the problems where I start off to the side and I write out the formula for the area of a square. And I know, of course, the formula for area of a square is side squared. Then you want to say to yourself, what's the dimension that I need? Okay, and that would be S. I need to know the length of a side in terms of this problem. Well, it says that each of these squares are drawn perpendicular to the x-axis. So I'm just going to draw in an example, okay, of my square. So I have something like this, okay? And so obviously my side is from here to here. That's my S. Okay, so the length of that side would be found by upper minus lower. So my upper curve here is g of x, and my lower curve is f of x. So I would say it's g of x minus f of x. And then the area formula would simply be g of x minus f of x all squared. Okay, now I'm just going to write that shorthand kind of off to the side, but then when I actually go in and plug in my volume formula, that's when I can go ahead and put it in appropriately, okay? So put in the actual functions. So now as I go ahead and do that, I can say that my volume equals the integral from, it's still 0 to 2, that's what's holding that on the x-axis, okay, of g of x, which was the 4 cos 1/4 pi x, minus f of x, which I have to put in parentheses, 2x squared minus 6x plus 4, all of that quantity squared dx. All right, and that was worth 2 points. 1 point for the integrand, 1 point for the limits. Okay, so let's go ahead and move on to the next question we're going to do. Okay, the second question we're going to do is 2012, number 2, and this is a with calculator question. And so I chose this one because it has a few different elements to it that I definitely wanted to review in the video so that if you come across that in problems, you're ready for them. Okay, so 2012, number 2, let R be the region in the first quadrant bounded by the x-axis and the graphs y equals natural log x and y equals 5 minus x, as shown in the figure above. So as I look at this, I can definitely tell that my curved function is y equals natural log of x, and my straight line is y equals 5 minus x. Find the area of R. Okay, so the reason I chose this one is because it's a little bit unique here. If I'm looking at this, I can't find the area of R completely by doing upper minus lower, because as I look here at my region, I have a couple different, I have a different upper and a different lower depending on where I'm looking in the region. So for example, when I am up until here, up until this point of intersection, I would say my upper is the natural log of x and my lower is the x-axis. And in fact, y equals 5 minus x, this line doesn't play a role in it at all. So I'm going to kind of draw that line in as a divider, okay? Then after I cross over that line, which of course is also where these graphs intersect, then I'm looking at this triangular region, which of course now my upper is the 5 minus x and my lower is again the x-axis. So I think the best way to approach this is to recognize that and to kind of break it up into the sum of two different areas. So I kind of have region 1 and region 2. So I'm going to call this region 1 and region 2. Okay? Now, a big part of this is being able to find that intersection point and be able to determine what that value is. So of course, I'm going to call that A, and I'm going to go to my graphing calculator, get these typed into my y equals natural log of x and 5 minus x, set my window up exactly as they have it. So I can tell here that I'm going from 0 to 1, 2, 3, 4, 5. You can go out to 6 if you want, and on my y-axis, I'm 0 to say 2. Okay, so you can go ahead and graph this and calculate that intersection point by doing second calc choice 5, and then come back to me with your point. Okay, so the intersection point I found was 3.693441359. Okay, and I went ahead and stored that as alpha A, and I hope you do as well. If you haven't, just pause the video and go ahead and store that into your calculator as alpha A. I really am asking you to do this along with me. I know some of you just watch and don't, but the practice of calculating all that kind of stuff, guys, if you are not able to do that on the exam, then you're kind of out of luck because I'm not going to be there to tell you that intersection point. All right, so now, like I said, we're going to kind of break this up into the sum of these two different regions. So I'm going to say the area of all of region R is equal to, first, region 1. So I'm going to say the integral from 1 to A of upper minus lower would be natural log of x minus 0 quantity dx, plus the integral from, now I'm going from A until 5, so from A till 5 of the line 5 minus x, again minus 0, dx. Now, do you need the minus 0? Absolutely not, okay? But if I'm just showing my upper minus lower for each of these, in this left-hand region, my upper minus lower is, of course, right there from the natural log of x to the x-axis, and on here, it's the line 5 minus x to the x-axis to the 0. Okay, so it is with calculator, so once I've written that formula out, I'm going to ask you to pause the video, type that whole thing in, and get an answer and come back to me and see if we agree on our areas. Okay, so I got an area of 2.986. I hope you did as well. All right, let's go ahead and move on to part B. Okay, part B says region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. Write but do not evaluate the expression involving one or more integrals. So I'm just going to get those labels on there again. Y equals natural log of x, y equals 5 minus x. And then, of course, this was divided up, and I had an a here. And I've already written down what my a value is, so I don't need to write that down again. And so the idea here is that we have these, it's a region R is the base of a solid. Remember, that should scream out to you, and you should know the formula is the integral from a to b of area dx. So what am I finding the area of? A square, and I am perpendicular to the x-axis. But once again, if I'm drawing in these squares, okay, I have two different scenarios. I have a square over here, and then I have squares over here, okay? And so, again, the length of the side of the square depends on which side of A I'm on. So if I'm between 1 and A, I'm going to have a different formula, upper minus lower, than I am if I am between A and 5. So again, I have to split this into two separate integrals and add them together. So what I want you to do right now is pause the video, write out your formula for area of a square, determine the length depending upon where you are on the graph, between 1 and A or between A and 5, and then the length of a side, that is. Then go ahead and write your entire volume formula. Then come back to me and see if we agree. So I'm asking you to do basically the whole problem, set it all up, and then come back and see if we agree. Okay, so take a look at what I have and see if you agree. So again, I broke this up into my two different cases, okay? So I have, first of all, the case of the left-hand region, and that would be from 1 to A. I said that the side length is upper minus lower, so natural log of x minus 0. So then the area would just be that side, which of course is just natural log of x, squared, okay? From A to 5, so this triangular region here, okay, these squares would have upper minus lower be 5 minus x minus 0, which of course is just the 5 minus x quantity squared for the area of those squares. So then I went ahead and put it into my whole volume formula. Volume is the integral, and I did, this is up until that blue line, up until A, and this is from A to 5. Okay, so for part B, we just had to get the expression. We didn't have to evaluate, so we are all done with that. As far as the point breakdown for this question, it is out of 3 points, as was part A. I don't know if I said that. So for this one, you get 2 points for the integrand, so 2 points for, again, for, I imagine, this piece here and this piece here. And then 1 for the expression for total volume, so showing that you're adding from 1 to A and from A to 5. All right, let's move on to part C, last question of the video. Okay, this last question says the horizontal line y equals k divides R into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. Okay, so we first have to go ahead and draw in that line y equals k. It does not have to even look like it necessarily divides it in half. You're just going to draw in a random line y equals k. Okay, and what you are saying about that horizontal line, so it's obviously across the horizon there. What you're saying is that these two regions, which I'm now going to label region 1 and region 2, have to be congruent. We want them to be equal. Well, if I look at this, okay, I am now dividing this in a different way. I'm now splitting this going up and down. So I'm now looking at this from here to here and saying I want the area from up until the purple line to equal the area up until my intersection point up here. So I want this region here to equal this region here. So I need to all of a sudden be talking, if I'm talking my bounds going this way up and down from 0 to the blue or to the purple line, which is k, and then from k to this y point of this intersection, the y coordinate of this intersection, then all of a sudden I'm in terms of y. So I need to write this all into everything in terms of y. Okay, and so I purposely chose this question because we don't do this very much, and we need to get better at it. All right, so in terms of y means First of all, I'm going to take both of the equations, y equals natural log of x and y equals 5 minus x, and I'm going to get them in terms of y, means I'm solving for x. So this first one should be very easy. You're just doing e to the on both sides, so e to the y is equal to x. And over here, I'm going to solve for x, so I'm going to add the x over and subtract the y. So basically x equals 5 minus y. Okay, so I have those two equations now in terms of y. So I'm going to write those up on my graph. So I have, instead of y equals, I have x equals e to the y, and over here I have x equals 5 minus y. Okay, so those are my two curve names. The other thing I need to do is find my bounds in terms of y. So obviously my lower bound here is 0, so that one's fine. And then I know my k here. So I have 0, I have k, and then I need to know this intersection point up here, which I'm going to call B. All right, so I need the coordinate of that intersection point, but I need the y coordinate. So hopefully you still have that in your calculator. Go ahead and recalculate that intersection point, and let's write down what B is. I'm going to ask you to pause the video and get that done and come back to me. Okay, so I've written down the B that I found, and hopefully you agree that the y coordinate of that intersection point is that 1.306, blah, blah, blah. Okay, so now what I need to do is write an area expression for region 1 and region 2. And what I want to do with these, when they say, these come up every once in a while, every few years, where it'll say, you know, a line y equals k or x equals k divides a region. The easiest way to do these integral, writing the equation to solve that would allow you to solve for k is basically setting up that region 1 has to equal region 2. Okay, so we're going to write an equation for the area of region 1 and for the area of region 2. So area of region 1 has to equal the area of region 2. Okay, now usually when we are doing the area formula, if it's in terms of x, it's upper minus lower. But now because we're in terms of y, it's going to be right minus left. If I draw my slices in, I would draw a slice from the right to the left for each of these. Okay, and so when I find my area formula, it's going to be the integral, so kind of write down in general, the integral from a to b of right minus left, and then it's dy. Okay, so that's what I need to concentrate on for both region 1 and region 2 here. Okay, so it's the integral from, all right, so region 1, well, I have region 1 actually labeled as the upper region, so it doesn't really matter. Let's do the one I labeled as region 1 is my upper region, and that would go from k to b of right minus left. So my right-hand curve is the 5 minus y, minus my left-hand curve is e to the y. And that whole thing would be then dy. Okay, so that's area of region 1. That has to be equal to the area of region 2, which is, of course, the integral from 0 to b of, again, right minus left. So 5 minus y minus e to the y, and again, all dy. Okay, so that's the easiest way, I think, to write it. You want to make sure that you are showing everything in terms of y. And the biggest thing that students struggle with is making your bounds in terms of y. So I had to find that new intersection point, that B, and then I had to remember it's right minus left. Okay, so thanks for sticking with me. Hope that was a good review, kind of a broad sweeping review of one without a calculator, so kind of, again, more practice finding integrals. And then also, you know, you saw a volume where you're revolving around an axis, a horizontal axis. Here we saw where you had to divide your region into 2 and add up for the volume and also for the area. And now this one where we had to draw on a line to divide the region into 2 equal areas. So we had a lot of different things going on here. Definitely in class we're going to practice a couple more different ones. You know, sometimes they're very straightforward, like our first one that we practiced tonight. And other times they have some different kind of catches to them, like this one, this 2012 one. So we don't know what we're going to see on the exam, and so we want to get you prepared for anything. All right, have a fantastic night, and I will see you in class next time.